Gokul Global University present webcast lecture. In previous two lecture, we discuss about different types of flip-flop like RS flip-flop, JK flip-flop, T flip-flop, D flip-flop, master slaves, and in a register, serial in serial output register, serial in parallel output register, parallel in serial output register, parallel in parallel output register, and all the working system and also diagram and time diagram. So today we learn about counter. Counter is based on flip-flop and register. Next, the many different types of counter are available, but today we only discuss about a synchronous counter, also known as a ripple counter. Introduction. Counter and register belong to the category of MSI, sequential logic circuits. They have similar architecture as both counter and register. Comprise a cascade arrangement of more than one flip-flop with or without combinational logical devices. Both constitute very important building block of sequential logic, and different type of counter and register are available in integrated circuit IC from are used in a wide range of digital systems. While counters are mainly used in a counting application where they either measure the time interval between two unknown time instant or measure the frequency of a given signal. Registers are primarily used for the temporary storage of data present at the output of digital circuit before they are fed to another digital circuit. We are all familiar with the role of different type of register used inside a microprocessor and also their use in a microprocessor based applications. Because of the very nature of operation of register, they form the base of a very important class of counters called shift counters. In a synchronized counter, external clock is applied to the first flip-flop and other successive flip-flop are triggered by the output of the descending flip-flop. However, in synchronized counter, all the flip-flop are triggered simultaneously by the external clock pulses. Next, a synchronized counter or a ripple counter. It is well known that if a clock of frequency f is applied to the clock input of a negative triggered T flip-flop, those T input is connected to high, means the logic 1 is toggled at the triggering edge of each pulse, shown in the figure 1.1 T flip-flop with the clock pulse and output Q. Next, the frequency of the output will be f upon 2 if two flip-flops are connected in series as shown in figure 1.2. The output frequency obtained will be division of input frequency by the factor of 4. This will have the 4 unique states 0, 0, 0, 1, 1, 0, 1, 1, showing the timing diagram of figure 1.2a. The frequency division is basically a counter. This circuit is called as 2-bit a synchronized counter or a ripple counter. In this way, any number of flip-flop may be connected in series. Next, a counter with n number of flip-flop will have 2 raised to n unique state, which will count in natural sequence, and the counter is called a modulus 2 raised to n counter, short mode counter also called. The modulus of a counter represents the total number of states through which the counter can move. The binary counter with one flip-flop will have two states, and the counter is called as a mode 2 or a divided by 2 counter. Reference figure 1.1. You see, the counter with two flip-flop will have four states, including 0. Okay, the counter is called as a mode 4 or a divided by 4 counter. Reference figure 1.2. Here you see the series T flip-flop. It will have 0 0, 0 1, 1 0 and 1 1 state. Similarly, mode 8 and mode 16 counters may be discussed. In this asynchronous counter or a ripple counter, all the flip-flops are not synchronously counted by the same clock pulse. As discussed about in asynchronous counters, external clock is applied to the first flip-flop and other successive flip-flops are triggered by the output of the preceding flip-flops. Further, it is well known that when an input pulse is applied to the flip-flop, it gives an output after some time delay, propagation delay so called. Consider a counter with a two flip-flop connected in a series, and if propagation delay of each flip-flop is 20 seconds, then the output of the second flip-flop will be obtained after a time delay of 10 seconds. Since each flip-flop is toggled by the changing state of the preceding flip-flop, the delay accumulated the number of flip-flops. That is, delay ripples through the flip-flop and become quite appreciable when the number of flip-flop is increased. This delay may become comparable to the period of clock or more than the clock period. In the condition, there is possibility that the first flip-flop responds to the new clock pulse before the previous pulse has effected transition of the last flip-flop. This may lead the skipping of certain count which is undesirable. So the asynchronous counter become too slow for carrying out the counting. If the clock frequency is large enough or the number of flip-flops are increased. Next, ripple counter with JK flip-flop. A ripple counter is a cascaded arrangement of the flip-flop where the output of one flip-flop drives the clock pulse of the following flip-flop. The number of flip-flops in the cascading arrangement depend upon the number of different logic states that is goes through before it repeats the sequence, a parameter known as the modulus of the counter. In the ripple counter, also called an asynchronous counter or a serial counter, a clock pulse is applied only the first flip-flop is called the input flip-flop. In the cascading arrangement, the clock input to any subsequent flip-flop comes from the output of its immediately preceding flip-flop. For instance, the output of the first flip-flop acts as the clock pulse of the second flip-flop. The output of the second flip-flop feeds the clock input of the third flip-flop and so on. In general, in an arrangement of the n flip-flop, the clock input to the nth flip-flop comes from the output of the n-1th flip-flop for n greater than 1. Figure 1.3 shows the generalized block schematic arrangement of an n-bit binary ripple counter. As a natural sequence of this, not all flip-flop change state at the same time. The second flip-flop can change state only after the output of the first flip-flop has changed its state. Next. That is, the second flip-flop would change state a certain time delay after the occurrence of the input clock pulse owing to the fact that it gets its own clock input from the output of the first flip-flop and not from the input clock. This time delay here equal the sum of propagation delay of the two flip-flop, the first and the second flip-flop. In general, the n flip-flop will change state only after a delay is equal to n times the propagation delay of one flip-flops. Next, the term ripple counter comes from the mode in which the clock information ripples through the counter. It is also called an asynchronous counter, as different flip-flop comprising the counter do not change state in synchronization with the input clock. In the counter like this, after the occurrence of each input pulse, the counter has to wait for a time period equal to the sum of propagation delay of all flip-flop before the next clock pulse can be applied. Next, the propagation delay of each flip-flop, of course, will depend upon the logical family to which it belongs. Okay. Next, propagation delay in ripple counters. A major problem with ripple counters arises from the propagation delay of the flip-flop consisting the counter. As maintained in the preceding paragraphs, the effective propagation delay in a ripple counter is equal to the sum of the propagation delay due to the different flip-flops. The situation becomes worse with increase in the number of flip-flops used to construct the counter, which is the case in larger bit counters. Come back to the ripple counter and increase the propagation delay. Put a limit on the maximum frequency used as clock input to the counter. We can appreciate that the clock signal time period must be equal to or greater than the total propagation delay. The maximum clock frequency therefore corresponds to the time period that equal the total propagation delay. Each n is the propagation delay in each flip-flop. Then, in the counter with n flip-flops having a modulus of less than or equal to 2 raised to n, the maximum possible clock frequency is given by the f maximum, means the frequency maximum is equal to 1 upon n cross TPD. Often, two propagation delay times are specified in the case of flip-flop. One for low to high transition TPLH, low to high, and the other is high to low transition LH TPLH. At the output in such a case, the larger of the two should be considered for computing the maximum clock frequency. Next, as an example, in the case of ripple counter, IC belong to the low power supply power restrict TTL, LS, TTL, family, the propagation delay per flip-flop typically is of the order of 25 nanoseconds. This implies that 4-bit triple counter from this logic family cannot be clocked faster than 10 MHz. The upper limit on the clock frequency further decreases with increase in the number of bits to be handled by the counter. A synchronized binary mode 16 counter. A synchronized binary counter or a mode 16 counter will 16 unique states and need 4 flip-flop. To design this circuit as a 2 raised to 4 is equal to 16. A series combination of 40 flip-flop is shown in figure 2.1, in which the output of first flip-flop is connected to the clock input of the second. The output of the second is connected to the input of the third, and so on. Next, the clock is applied to the clock input of first T flip-flop and T input of all the flip-flops are connected to high logic 1. The clear terminal of all the flip-flops are connected together to clear, which reset the counter when logic 0 is applied to clear. Here you see the figure of T flip-flop join in series. Next, it is well known that a T flip-flop toggle at the trailing edge of the clock pulse. So first flip-flop changes its state each time the clock input goes from high to low. This is the diagram. Next, the subsequent flip-flop change state when their input change from 1 to 0. The waveforms at the input and output of all the flip-flops are shown in figure 2.2, while the state of flip-flop corresponding to input clock pulse are given in table 2.1. In the asynchronous counter, one can use JK flip-flop in place of T flip-flop. The J and K input of JK flip-flop may be tied together, which works as T input. The ripple mode 16 counter designed using JK flip-flop is shown in figure 2.3. Here you see the 16 counter with JK flip-flop and table. Okay. Next, synchronized down counters. So far, the counters which count in the forward direction are considered. Sometimes it is also desirable to have the digital counters which count in the backward or a reverse direction, like a 3 2 1 0 and again 3 2 1 0, or a 1 1 1 0 0 1 0 0 1 1, like this. So the figure 3.1 show the logic diagram of a synchronized move or counter, down counter. In the up counter or a forward counter, the external clock is applied to the first flip-flop and other successive flip-flops are triggered by the output of the preceding flip-flop. In the down counter, the external clock is applied to the clock terminal of the first flip-flop, as in the case of the up counter. The other successive flip-flops are, however, triggered by the Q outputs of the preceding flip-flop. Next, the output are taken as Q's output. The output waveforms of this counter are shown in figure 3.1b, which are in the down sequence. Here you see. Next, a synchronized mode 16 down counter. A synchronized mode 16 down counter will count in the down sequence having 16 destiny state. It need 40 flip flop as 2 raised to 4 to 16. The down sequence will be 15, 14, 13. It may be designed in the similar fashion as a mode for down counter. Figure 4.1 show the down counter in which external clock pulse is applied to the T0 input of first flip-flop. Next, here you see the figure. The 0 Q output of first flip-flop is connected to T1 input of second flip-flop. Similarly, Q1Q output to T2 and to Q output to T3. The circuit may also be designed with the JK flip-flop as shown in the figure. The output waveform are shown in figure 4.3, which corresponding to down or a reverse counting. The Q0 output will toggle at the triggering edge of the clock pulse, and Q1 through Q3 will change their output at the triggering edge of the Q output of the preceding flip-flop. Here the time diagram. Next, the state of flip-flop output in the reverse sequence are given in table 4.1. Here you see all the clock pulse and the output count. Next, a synchronized mode 16 up or a down counter. Okay? Up or a down counter. A counter can work both as up counter and down counter, up or a down counter. If AND or control gates are used for connecting the Q's and Q's output of the preceding stage to the input of the next state. Here in this figure you see AND or control gates. Next, figure 4.1 show the circuit for a mode 16 up or a down count or synchronized counters. Here the T flip-flop are used along with AND or control gate. In this circuit, when control input up or down is high, the counter work as up or a forward counter as the output Q0, Q1, Q2 gets connected to the T input of the next stages. Again, when up or down input is low, the counter works as down counter as the complemented output gets connected to the T input of the next stage. Next, figure 4.2a and b show the waveform taken the Q output of up and down counter respectively. Next, the counting sequence are shown in table 4.1 for working the circuit as up or a down counter. Here you see. Next, in the next lecture we will discussing another counter. Okay friends, thank you for watching.